The final lesson of the year will be on query packages, or language integrated query. And the reason we're covering this topic is to provide you with conceptual and technical tools to manipulate data conveniently, whatever language you're working in. So let's back up a little bit and talk about tabular data. In Julia, the type for storing tabular data is called a DataFrame. And here's a standard dataset on cars that's contained in the Vega datasets package. So Vega is a JavaScript data package that you can use to build data visualizations for the browser. And Julia has some tools to connect up with Vega. So here's what the dataset looks like. We have each row representing a car, and each column representing a specific feature of each car. So for example, a Chevy Impala gets 14 miles per gallon. In Python, the standard DataFrame object is also called DataFrame with the same capitalization, and it's in the pandas package. And in R, you have a supplied DataFrame type called data.frame, and in R, this dot is just another letter in the language. So this is just a spacing character. But this data structure has some drawbacks. So there's another one that you'll often use called a Tuples, which is like a play on table. And that's a part of a suite of packages called the tidyverse packages that are all designed to work together and make working with data as convenient as possible. So the way you typically learn of interacting with data frames, performing manipulations on them, is to primarily work with columns. So we vectorize our computation by selecting out columns and then describing the operation that needs to be performed on those columns. So for example, problem 1 asks us to make a Boolean array with the same length as the columns of data frames, where the value in each position is 0 if the car does not have 8 cylinders and 1 if it does. So we'll index the data frame. We'll use a colon to say let's select every row, and then for a data frame, instead of using a numerical index, we can use a symbolic index, and that will grab the corresponding column. So we're selecting out the cylinders column here. And we get a vector which has some 8s in it and some numbers which aren't 8. So to get the trues and falses we're looking for, we element-wise compare it to the number 8. Then the second part of the question says, use that array to return a data frame containing only the rows where the entry in the column is equal to 8. So we'll index the data frame with this Boolean array. So it's going to select only the rows where the value in this Boolean array is true, and that's what we want. Now we have only those cars that have 8 cylinders. So this is fine. You can certainly get by operating in this way, but it's not ideal in the sense that we have to do a lot of thinking about vectorization, so handling entire columns at once, and then indexing. We have to remember where to put the right indexing operations. It would be better if we could just express the idea, get every row where the cylinder column says 8. And for databases, which are the standard industrial way of storing tabular data, there is a good solution to this problem. It's called SQL, or Structured Query Language. And you can write a query like this, which says, select everything from the cars database where the cylinders column is equal to 8. So other than this asterisk, this is pretty much just English. And you're expressing your intent to the database and letting it figure out how to perform that computation. So this is different from what we did above because we specifically told the system it needs to compute this Boolean array, and then it needs to use that Boolean array to index the data frame. So the idea of language integrated query, or a query package, is to bring these two things together. We'll have access to a query language inside of our language, so we can use instructions analogous to this very nice SQL query for data frames or for other objects within the programming environment that store tabular data. I like the term language integrated query because it describes exactly what we're trying to do here. However, if you use that terminology with programmers, they'll be thinking about Microsoft, because that term was introduced in 2007 for a particular set of features made available to the .NET languages. And here we have in mind really similar tools that are available in Julia, Python, and R. So this happened first in R in a package called dplyr, the second version of which is called dplyr. And people recognized that this was really a valuable idea, and it was adopted in Julia in the form of a package called Query. And pandas doesn't really have an analog to these packages, but pandas does supply enough constructs to allow you to do some comparable things to manipulate data frames in that package as well. So let's look at a few specific operations and see how things work in Query, the Julia package. And you'll be able to translate these ideas very directly just by learning the syntactic differences to R, and with a few more changes to Python as well. So here's how a filter query looks. We want to select only those rows for which the cylinder column value is 8. We start with the data frame, and then just for convenience we use this pipe operator, which forwards the object returned by the previous expression as the first argument in the next function. So this filter macro is designed to take a data frame coming in from the left. And it takes an anonymous function. So this is the function which takes a value x and accesses the cylinders field of x and compares it to 8. And then this returns a raw object that's designed to be piped into more operations. So if we want to go ahead and display it as a data frame, we pipe it into the DataFrame constructor. And we get the same result as before. We only have the rows whose cylinder column value is equal to 8. And to crack open the hood a little bit, what's going on is that the filter macro takes its anonymous function and it applies it to each row, and that row is being treated as something called a named tuple. So this is a construct that's available in Julia and Python. And the idea is that it's like a tuple, except instead of accessing the fields of that tuple with indices 1, 2, and so on, you give them names that you can use later. So for example, A and B in the case of this little named tuple. And then you can access the A field in the way that you would normally do that for an object, t.a. So a row in a data frame is very naturally thought of as a named tuple, where the names are the names of the corresponding columns, and then the values are just the entries in the table for that row. So you might have noticed the one thing that was a bit clunky about what we did is that we have this anonymous function. We always have to write x maps to x dot whatever, and that's clearly not as succinct as it could be. So Query introduces this other anonymous function syntax, which is actually relatively common in the programming world, where you use an underscore to represent the argument. So this is very much analogous to what you do in algebra when you say something like x squared plus x. Everybody knows when you say that, you mean the function which takes an input x and returns the square of x plus x as the output. Same idea here. This is a programming analog to x. So it just says whatever the row is, access its cylinder field and compare it to 8. That's the anonymous function that should be supplied to the filter macro. And notice that this is not a general Julia construct. This is available specifically when using query macros. So in problem 2, we're asked to write a query statement which filters the data frame above so that we only retain rows that have a displacement greater value than 300 and a horsepower greater than 500. So we take the data frame and we pipe it into filter, and the anonymous function we'll use just says grab the displacement value for this particular row and compare it to 300. And notice that we don't have to do any array things. This is being applied row by row. And in pandas or in R, you would not want to do that, because anything performed row by row, if there happen to be very many rows, which there often are, is going to introduce a performance problem. In Julia, there isn't a performance problem. The dplyr package in R does hide this from you. So you will be able to do something very similar. But it's worth being aware if you're performing row by row operations manually in Python or R, there can be performance issues there. And then we'll collect that into a data frame. And there's our solution. We have only large values in the displacement and horsepower here for the remaining cars. So filter is one of the fundamental data frame operations. You'll use it a lot. And together with the remaining data frame operations we'll identify in the rest of this lesson, it performs sort of a core set of common data frame operations with which you can do pretty much anything you need to do when it comes to manipulating data frames. So the second one is sorting. This is a common thing with spreadsheets. You're looking at a spreadsheet of data, you want to see what's going on with respect to a particular column, you might sort by that column. So in the query package, the order by macro is the one that does that. And just like you would think, it takes an anonymous function and then just sorts the rows based on the value of that anonymous function evaluated on each row. And here we're going to throw in an extra macro called take, which says just grab the first few rows. So this is common when doing interactive work, because sometimes you just want to see what's going on at the top and you don't want the printed data frame to continue to occupy a lot of vertical space on the screen. So here we're piping the data frame into the order by macro, pulling out just the value of the displacement field, and then taking the first 5 and looking at what we get, and it looks something like this. So we can see that these are the 5 cars with the smallest engines. So displacement is engine displacement volume. So problem 3 says write a query which sorts by weight in descending order. So we want to take this weight in pounds column and order by that. So there are 2 ways to do that in the query package. We can do order by underscore descending, which is just a related macro to this one. It's just for convenience. Or we can negate the weight in the anonymous function, because multiplying every number on the real number line by -1 completely reverses the order of the number line. So if we select the weight in pounds corresponding to that particular row and then multiply by -1 and sort by that, then that gives us the order that we want. So the smart printing here ended up suppressing that particular field, weight in pounds, but these are the 5 biggest cars by weight. So far we have filtering, we have sorting. The third core data frame manipulation is selection. And here we're talking about excluding columns. So filtering is excluding rows, selecting is excluding columns. And there are a few conveniences for determining which columns to use. You can just specify the name directly as a symbol. You can specify numerical index, or you can write a predicate, in other words, a function that returns a bool that's going to be applied to each column name, and if it returns true, that column is retained, and if it returns false, it's rejected. Or you can put a negative sign directly in front of the symbol, and that specifies that that particular column should be dropped. So for example, we can say select 1:3, so that's going to select the first 3 columns, and then also the displacement column, and then drop the miles per gallon column. So that's necessary here because that's in the first 3 columns and would otherwise have been included. And then anything that has EAR appearing in the symbol name, keep that as well. And collect that as a data frame. And what we see is that we get name and cylinders because those are among the first 3 and neither is miles per gallon. Then displacement, which is specified here, and then year because that included EAR. And nothing else did, so we only get that 1 column in that position. So problem 4 says, let's write a query to return a data frame containing only the SOBs, sorted by horsepower, and showing only the name, number of cylinders, and year. So we're putting together some ideas now. So start with our data frame, and then we'll pipe it into a filter macro to get only the SOBs. So to check whether it's a SOBs, you notice the value in this field, the name field. It might say SOB, but then some other stuff too. So we don't want to have to go through manually and look at it and see what all possibilities there are involving SOB. So we'll just check whether SOB occurs in that name. So here we're grabbing the name of the current row, checking if SOB is in there, and then we're filtering based on that. And then we're going to sort by horsepower, and then we're going to select only the name, the number of cylinders, and the year. So we see that there are 5 SOBs. All of them are 4-cylinder. Here they're appearing in increasing order of horsepower, and we're only getting the name, cylinder, and year. So here's another example of a data frame, and here we're going to have many more columns than we did in the cars data set. Let's say you're looking for a relationship between hair color and various genes. So you might have 200 genes. Indicated here is gene 1 up to gene 200. And response variable like hair color. You're trying to understand something about the relationship between these genes and hair color. Maybe there's a few specific genes that influence this hair color, and you're looking for that relationship. And the goal is to write a query which just pulls out these columns. So in this case, we'll actually get the same data frame back because they just all have the word gene in them. But you can imagine that there are many other columns here in a real data set, and you're trying to pull out just these 200. So what we'll do here is supply a predicate, and in this case, we can just say occurs in gene. So that will be treated as an anonymous function which takes a symbol in and returns true or false according to whether that symbol contains GENE somewhere in the string. So recapping, we have filtering, sorting, selecting, and now we'll introduce a 4th operation which is mutating. And that's where we introduce new columns which are derived from existing columns. So for example, you might want to compute the engine displacement per cylinder. So the engine displacement measures the total volume inside the engine, and you might want to normalize by the number of cylinders so that you're talking about the size of each cylinder. And the term for that in dplyr and also in query is mutate. So we pipe the data frame into the mutate macro, and we use this keyword-like syntax where we have a new name on the left, then an equal sign, and then an anonymous function that's going to be applied to each row, and the value returned by that function is going to be the value stored in that particular row in the new column. So we call it displacement per cylinder, and we compute it by pulling out the displacement field of the row and the cylinders field of the row, dividing, and returning that value. So here we have displacement per cylinder for each car. So we have all of the columns we did before, and then also this new one. So problem 6 says write a query which returns a new data frame showing a miles per gallon per pound value for each row. So we're cutting heavier cars some slack for their lower miles per gallon value, and we want to say, okay, per pound that you have to drag around, what's your miles per gallon? And we want to only include rows where that value is at least 0.005. And we want to only be showing that new value we computed together with the name and the acceleration. And finally, let's just print the first 5 values. So we're starting to see here the value of using the pipe operator. We can really separate these operations out line by line. So first of all, we want this new column, so we'll use the mutate macro. and maybe we'll call it M per G per pound. And to compute it, we pull out the miles per gallon divided by the weight, and then we're supposed to only include the rows where this newly computed value is greater than 0.005. So notice here we're piping in the output of this previous macro into this one. So it will have access to this newly computed field. We're not reaching all the way back to the original data frame. And that's really important. You want to be able to change the data frame and then change it again in a different way and just stack those changes on top of each other and not have to continue storing the result of the new computation as another variable. Then we're supposed to choose only the name column, the acceleration column, and the miles per gallon per pound. Then we take 5 and then collect that as a data frame. So here's our miles per gallon per pound field that we calculated, and we also have the name and acceleration for those particular cars. And notice that indeed we only have mpg per pound less than 0.005 for these 5 rows. So we've seen examples now for filtering, sorting, selecting, and mutating. And next we'll tackle grouping and its closely related cousin, aggregating. So conceptually, grouping is a bit trickier because it changes the structure of the table. The way you want to think of it is sort of like a bunch of filtering operations together. So for example, we might group on the X column for this particular small data frame. And in that case, X has only 2 values, 1 and 2. And all of the rows corresponding to an X value of 1 get grouped together. And all the rows corresponding to an X value of 2 get grouped together in a separate data frame. So here we're going to get a collection of data frames. This is stored internally as something called a grouped data frame. So you can visualize this as like a stack of cards. If you think of a data frame as like a table written down on a card, then here we're introducing essentially an extra dimension where we have like a stack of these cards. And the groups are indexed by the value that they were grouped by. So we have keys here, 1 for the data frame where all the X values are 1, and 2 for the data frame where all the X values are 2. So this grouped data frame is not just a stack of cards, it's an indexed stack of cards where each one carries this extra bit of information, which was the grouping value for that card. And then the difficulty with this grouped data frame is there's not a particularly good way to present it. And often the purpose of grouping is to do something with each of these groups, compute some sort of summary statistic, and that's called aggregating. And the term for that in the Julia package query is map. So for example, we might want to say what is the sum of all the y values for each of these groups. So for each one, we'll go through and add up the y values. In this case, we get 3 plus 2 plus 7, which is 12. And so we would say the group corresponding to x equals 1 has a sum of 12. And the group corresponding to x equals 2 has a sum of 6. So if for each group we extract its key, so G here is representing the group, then for a key of 1 we have a sum of 12, and for a key of 2 we have a sum of 6. So these grouping and aggregating operations will most commonly be performed in conjunction with one another. So for example, suppose we want to see the weights of cars based on the number of cylinders. So here's a really clunky way to do it. We take our data frame, we group by the number of cylinders, and then we aggregate and return the number of cylinders as one of the new columns in our data frame. So we'll see there's some 8-cylinder cars, some 4s, some 6s, and a handful of 3s and 5s. And then for the weight values, let's just return the entire weight in pounds vector. So we can see that for 8-cylinder cars, these are all of the weight values for the cars with that number of cylinders. Same idea for 4 and 6. 3 and 5. And of course, typically you don't want to present a table that looks like this because we have essentially tables as entries of this table. And it looks pretty bad. It's not likely to be useful. What we would normally do instead is summarize this in some way. For example, we might want to know the average weight of an 8-cylinder car or the average weight of a 4-cylinder car. So we'll just be distilling this big vector down to a single number. So the way that works is we'll just put in an extra function to apply to this value, weight in pounds, a function like sum or mean, which boils down a vector to a single number. For example, we might look at the total weight in pounds. Perhaps more useful would be the average weight in pounds. So just glancing at this, we can see that 8-cylinder cars are bigger on average than 6-cylinder cars, which in turn are bigger on average than 4-cylinder cars, and that makes sense. And notice the curly braces here. In the syntax, that's just a special query thing. If you're combining this keyword syntax with the anonymous function stuff, they needed to put the curly braces in there for some technical reasons. And so the way this works is we pipe the data frame into this group by operator that just computes this value for each row and then stores a grouped data frame where the grouping is done based on the values returned by this anonymous function. And then we pipe that into the map macro, which is going to aggregate, and it computes for each group. So remember, this is operating now on a grouped data frame. For each of those groups, it computes the key of that group and stores that as in cylinders. And it computes the mean of the weight in pounds field and stores that as total weight. So notice that what's going on here is a bit different from what we've seen before, because the underscore represents one of the data frames in the grouped data frame. So one group. And extracting the weight in pounds field from a group produces an entire vector. And so mean is operating on that vector. So this is a little bit different than when the underscore was representing a row. Same idea here. This is representing the particular group in the grouped data frame, and we're pulling the key out. So key is a special function that identifies the value that we grouped on for each group in the grouped data frame. So problem 7 says, let's write a query which shows the average engine displacement based on country of origin. So we're going to group by the country of origin and then work out the average engine displacement for each of those groups. And then sort the resulting table in decreasing order of average displacement. So that we can just focus on one thing at a time. So we group by country of origin. And then the aggregation we're supposed to perform reads the average displacement, which is going to be the mean of the displacement column for each group. And then we also need to keep up with the country value. And that's going to be the key of each group. And then we'll order by the average displacement, and we're supposed to do it in decreasing order. So we need to negate the average displacement or use order by descending and then collect that into a data frame. So the US cars have the largest average displacement by far, and Europe and Japan are pretty similar and quite a bit smaller. So that rounds out the set of core data frame operations that involve a single data frame. There's filtering rows, there's sorting rows, there's selecting columns, there's mutating to create new columns, and then grouping and aggregating. And the last operation we'll talk about is the only one that involves two data frames. It's called the join. So suppose we have these two data frames, one called people, which tells us for Alice, Bob, Charlie, and Deborah, their age, and also their favorite Beatles album. And then we have this other data frame called albums, which says for various Beatles albums the year in which that album was released. And say we want to try to understand something about the relationship between the age of each individual and the year that their favorite Beatles album came out. So clearly that information is being stored across these two tables. And we want to put those tables together somehow to combine that information. So again, we have the people, their favorite album, and then this information for each album storing the year that that album was released. In other words, we really kind of just want to use albums as a dictionary, as a lookup table to compute an extra column for this people table. And the syntax for that, it looks a little funky, but what's going on conceptually is not too complicated. So the way it works is we take the original data frame and we join it to this second data frame, albums, that we want to use as a lookup table. And then we specify the columns from the first and second data frame respectively that should be compared for equality. So we want to say the album column in the people data frame, that should be compared against the name column in the album data frame. So if you see Yellow Submarine here, that should be linked up with Yellow Submarine here. So again, we're using the two data frames we want to join. Then we're specifying the column for the first one and the column for the second one that we want to use for comparisons. And then we'll use curly braces again with this keyword syntax to say which columns we want in the data frame that gets returned. And notice here we have to specify first data frame or second data frame, and the syntax for that is double underscore for the second data frame and single underscore for the first data frame. So we'll say, okay, let's get the name from the first data frame, so the name of the person, and the year of the favorite album, we'll make a new column for that, and we'll just grab year from the second data frame. And so we get exactly what we want, each person's name and the year of their favorite album. If we also wanted to include their age, we'd put a single underscore since that's coming from the first data frame and pull out the age field, and we would get that as an additional column. We could also specify the name of the album as well. We could do that by grabbing the first data frame's album field or the second data frame's name field. So the last problem asks us to write a join query to answer the question, what is the average price of the items purchased by each person? So we have here some purchases made by Alice, Bob, Charlie, and Deborah. So notice the names get repeated because each person made multiple purchases. This SKU, that's an identifier for a particular product. So Alice checked out, she bought 2 products, Bob bought 3, and so on. And the table that stores information about the goods, specifically just price information in this case, is called goods. So we want to use this goods table as a lookup table to supply an extra column for the purchases table. So we'll take the purchases table, we'll pipe it into a join operation with the goods table, and in both cases what we want to use is the SKU. So pull out the SKU value from the first table and the SKU value from the second table, so they have the same name in the 2 tables, and then get the name from the first table, so the person's name, and then the price from the second table. So for each purchase now, we have the person's name and then the price of the good that they bought. But then we're asking for the average price of the items purchased by each person. So we need to somehow put this together, put these 2 Alice rows together and compute an average of the prices. Put all 3 Bob rows together and get an average of these prices and so on. And the operation for that is a grouping operation. So we can group by name, and that returns a grouped data frame. And then we want to aggregate that by, first of all, retaining the name, and then computing the average price. And the average price for each group we can get by pulling out the price column for that group and then taking the mean. And then finally we collect the results as a data frame. So these are the average prices of the goods bought by each person. So hopefully if you have experience dealing with data frames in a way that's heavily index oriented, you can see that there's some convenience and composability that you get out of combining these pipe operations with these macros, which allow you to directly express the intent of the operation you want to perform.
So I just want to conclude by taking a look at this Julia Python R cheat sheet, and specifically in the row on data frames and query packages. So in the first column, we have an example showing how to use query in Julia, and we have filter, order by, select, mutate, group by, and map. And the analogous operations in R are performed in a very similar way. Some of them have different names. You have a range rather than order by, and you don't need the @ sign because these are not macros, they're just R functions. And the pipe operator has these % signs around it, but basically it's very similar, very clean, and that makes sense because query was based on this library dplyr that's being used here. In Python, things are a little bit different. What you see is we can achieve a similar effect to this piping operation by putting one method call after another. So we first call .query, that's a filter operation. We have to build this query as a string, and then we call .sort values on the result returned by that. And that's why we need this outermost set of parentheses here and here to make sure that the evaluation doesn't terminate at the end of the line. This one is not a method call. If we want to select, we have to do that by indexing a list. But then assign works very similar to mutate. We do have to put the anonymous function here explicitly. Grouping, again, works similarly, except you have to use a string. And aggregate, similar idea, use a dictionary instead of keyword syntax. But you can achieve the same effect.